Okay, so improper integrals, we're just going to do part one today. So an integral is called improper when the interval is infinite and also when f has an infinite discontinuity within the a to b that we're looking at. So what we're going to look at right now are the really obvious improper integrals. And the reason these are really obvious ones is because you're going to see an integral where it goes from like something to infinity, or negative infinity to something. And it seems like you can't take an integral when you're going from 1 to infinity, because it seems like that should always be infinite, but it's not. Okay, so if we have like a function like a 1 over x squared type thing, what that graph looks like here, I'll try to do an okay sketch. It looks something like this. And we're trying to find the area under this curve from 1 all the way to infinity. Okay? So if we're trying to find the area from 1 all the way to infinity, it seems like, okay, I'm always adding more area because it's always above the x-axis, so the answer is going to be infinity. It's not always going to be infinity, and I treat this like the pizza problem. If we're doing our pizza problem here, let's say we start with one pizza, and then we keep cutting it in half, and we do another half a pizza. And then we cut that in half again, we get how much more pizza? A quarter. And then we do another half of the pizza, which is an eighth, and another half, which is a 16th. And we continue to do that. Okay, we've got one full pizza here. And then we're taking our second pizza, and we're constantly cutting it in half. So we've got this full one. We've got half of this one. Sorry, that's close enough. Half of this one. Half of that one. What's going to keep happening as I cut it in half? How many pizzas am I going to end up eating? I'm going to eat 2 pizzas at the end. That sliver is just going to keep getting smaller and smaller. You can keep adding numbers on, and it can still equal 2. Okay? So that brings me to my really, really funny joke. You guys ready? I can't tell this joke to people because nobody understands it. But it's pretty much like the pizza problem, only it's a little bit inappropriate, okay? So there's an infinite number of people who walk into a bar. Ready? Okay, so first person, they order 1 beer. And then the second person goes up and they order half a beer. And then the third person goes up and they order a quarter of a beer. And then the fourth person goes up and they order an eighth of a beer. And the bartender goes, hold up, okay, all right, I get it. And he puts 2 beers on the counter. And these, infinite number of people go, oh, how are we supposed to have a good time with 2 beers? And the bartender goes, know your limits. Thank you, Colton. Thank you. Isn't that a good one? I try to tell that to like anyone who will listen, and no one understands my joke, so I can only tell it in this class. So I'm sorry, I had to tell an inappropriate joke today. Yeah, feels kind of good. It's like exciting, you know? Yeah, so anyway, what that tells you is that even bartenders are good at math sometimes. Don't report me. He wouldn't understand the joke. Oh, it's so embarrassing. I tried to tell that to another math teacher once, and they just, like, because my husband doesn't understand math at all. And I told him the joke, and I was trying to explain it to him, and he's like, no, it's not funny. And I was like, it is funny if you understand it. And he's like, no, I think I understand it, it's just not funny. So then we saw a math teacher, so I told them the joke, and they're like, I don't get it. And I was like, oh, so frustrating. You have a good joke you can't use. I don't have very many good jokes, so. Okay, that is one of them. Leave me alone. Okay, so what we're going to do for these, if you look down here, it kind of tells you. If we're going to infinity, we're going to replace that infinity with a letter. In this book, they use t. And then we're going to take the limit as t is going to infinity, and we're going to solve the integral that way. Because you can't plug infinity in and then plug 1 into this. So if we're doing that antiderivative, well, let's start with switching this to go from 1 to t. And then we're going to end up taking our limit as our t is approaching infinity. So that's your first step, is just writing it like that. Then we're going to actually do our antiderivative. So what is our antiderivative here? So it's negative 1 over x is what it turns into, right? Because this is x to the negative second. So you add 1 to it, it turns into x to the negative first, divided by negative 1. So that's this, right? And then we'll still have the limit out front. You don't want to lose your limit until you actually plug in your limit. So some of us need to work on our notation if we want to get full points on our AP test, which is obviously optimal there. And then we're taking this from 1 to t. So I'm going to plug in t, subtract, plug in 1, and I'm just going to leave that limit out front. So plugging in the t, we get negative 1 over t. And then subtract and plug in your 1, and you get negative 1 over 1. So that turns into a plus 1 back here. Okay, what is this piece going to as my t goes to infinity? 0. So I have 0 plus 1. So the answer to this integral is 1. So if I find the area of this shaded region that goes on forever there, that area would actually add up to 1. Kind of like our pizzas added up to 2. So questions on that part? Okay. So then you do the same idea with these other ones. So if we look at these other ones here, we have negative infinity to a value. You will replace your negative infinity with a letter, and then you take the limit as that letter approaches negative infinity. And the hardest ones are these ones where it goes both sides. It goes negative infinity to infinity, so you're trying to find the area all the way to the left, all the way to the right. What you want to do is you want to split that up, and you want to go from negative infinity to a number. And usually I just pick that number to be 0 because it's the easiest thing to plug in. But you could pick any value there. And then you'd take the integral from 0 to infinity. And then you would replace the negative infinity with a t. So you'd solve this problem like above, and then you would do the same thing here. You'd replace your infinity and solve this problem like above. So then you would kind of turn it into 2 problems. But you could pick this value being anything. 0 is just the easiest, so that's what we'll use in class. So any questions on the idea of it here? You can use that joke, but no one's going to get it, so sorry, guys. Okay, next page here. These 2 words they're like crazy important in AP Calc BC. Your AP test for the BC questions are, and I shouldn't say the majority of them, but a lot of them involve, is this convergent, is this divergent? So those are the things that you're going to see on Chapter 3 and Chapter 4 test a lot. So convergent just means that it actually goes to a number. Divergent means it maybe goes to infinity, so it diverges, limit does not exist of it. So we're going to go ahead and do this. Sometimes you'll get divergent ones, sometimes you'll get convergent ones like we did on the first one. So let's do this problem. Determine whether the integral given is convergent or divergent. So we're going to replace that infinity with a t, and then we're going to do the limit out front. So let's just start by writing the question. And especially in your notes, that way you do it when you get to your homework, write them out thoroughly here. And I'm just going to continue to use t, but if you have a favorite letter, you can use that. You like L? So it looks like a 1? Yeah, that's a good idea. Then you know the answer. It's easy. Yeah, it's a good idea. Okay, so we're going to take the limit as t approaches infinity. We got our 1 over x dx here. What is the derivative of that? Natural log, right? So we got natural log absolute value. Again, here I think we'd be okay without the absolute value because we're going from 1 to infinity, so they're always positive. But I just write it because then it's mathematically correct. Okay, so we plug in the top, we get natural log of t, subtract, plug in the bottom, natural log of 1. What is natural log of 1? 0. So that piece you can kind of cross off and not even think about. What happens to my natural log function as I go to infinity? It's going to go to infinity, isn't it? Okay, if we were approaching 0, then it would go to negative infinity if we're approaching 0 from the right. But we're approaching positive infinity, so our values continue to increase and increase. So this one actually goes to infinity. So instead of writing equals infinity, I'm going to write does not exist, because then if I messed up my sign, I don't miss anything. I don't miss my points here. So if it does not exist, then determine whether it's convergent or divergent. So then we will say that this integral diverges. So it's divergent. So any questions on that? Okay, and the hardest part I would say about this lesson is sometimes when you're trying to evaluate the integral, you have to use a U substitution or integration by parts, or partial fractions can now come up. So you just have to try to solve the integrals. And I'd say that's probably one of the hardest things about Calc 2 in general is it's not just like, oh, I'm doing a U substitution section, so I'm going to use U substitution on all of these. You're just given integrals, and you have to try to figure out how to solve them. So that's what we're going to be doing on this one here. So first thing you're going to do is replace this with your t. And I'm just going to do some scratch work on the integral part of it. And then I'm going to write my stuff mathematically correct. So I'm going to be going from t to 0 of x e to the x dx. What do you think we're going to have to use in order to solve that integral? Integration by parts. So our integration by parts, we should know it, but that doesn't mean we do. So the integral starts as the integral of what times what? U dv, and then that's equal to what? So u times v minus the integral of v du. Okay, so you might want to write that down just as a little refresher. Do you have a question, Seth? Oh, come on. Yep, so it's the integral of u dv, and that equals u times v minus the integral of v du. Okay, so we're going to use that here. We got to first figure out what our u and dv are. So for this problem, our u is equal to what, and our dv is equal to what, and then we use those to find our derivative and our antiderivative here. So out of these pieces here, where should I put the x so that it becomes more simple, for the u or for the dv? For u. So we're going to put x here. So that means I'm going to put e to the x dx back here. So when I do the derivative of x, I get dx, right, 1 dx. And take the integral or antiderivative of this here, and I just get e to the x. So now when I'm doing this, it's going to turn into u times v, so x e to the x, minus the integral of v du, which is e to the x dx. And this is still going from t to 0, so I'm okay to leave that on there. But I suppose that this is also going from t to 0, so I'm just going to leave them off. I'm not going to write equals either because I'm not keeping the limits on there. Okay, so if I actually finish this part out here, I end up with x e to the x minus e to the x. And I would have a plus c. Am I really in need of the plus c for this problem? No, because I've got limits on there, so I'm going to leave it off. Notice I'm not writing anything equals anything, so this is just my scratch work, okay? So now if we go back up to here and we actually start the problem, we've got our scratch work done so that we can just plug things in easier as we're moving. So we're going to take the limit as t approaches negative infinity. Oh yeah, sorry. I'm working on it, you know. There, is that good? Okay. They just can only see the bottom part, so that's why I'm trying to keep it so they can actually see what I'm writing. Okay, so we're taking the limit as t approaches negative infinity, and we've got the integral from t to 0 of x e to the x dx. So that's like my original, just replacing the t in there. And I give you points just for writing that step, so if you don't know what to do, at least get that one down. Okay, and that's equal to what I just came up with here, x e to the x minus e to the x. But we need the limit out front until I take it. And I'm evaluating that from t to 0. Okay, now I haven't taken the limit yet, so I'm going to keep my limit on here. And if I plug in 0, I get 0 here, and this turns into what? Negative 1. Okay, so plugging 0 in, I get negative 1. And then subtract, and plugging t in, we just replace the x's with t's. Okay, so we got to take the limit of this. Can we see that still okay? Let me, I think that'll work, right, Emma? Okay, so now we have to take the limit of all of these pieces here, and this piece is probably the hardest, so I'm going to do those other pieces. Obviously, this is just negative 1. This turns into plus e to the t. What happens to my e to the t as t goes to negative infinity? So this, you could think of it as like e to the negative infinity, which is the same as 1 over e to the infinity. And that sometimes helps without having to think about it graphically, but you could also think about the graph of it if that helps too. Because e to the t is just an exponential growth function. And as t goes to negative infinity, it goes to 0. So you can think about it as the graph, or you can think about it like this. Either way, you get 1 over infinity here, so we get 0. So this piece goes to 0. So then we still have to find this piece in here, which is the hardest piece, obviously. So let me just put equals 0 here. Okay, so this piece here I'm just going to write down below. We're taking the limit as t goes to negative infinity. And I can't just do this because I get a negative infinity, and this would move to the denominator and be an infinity. So let's actually try to write it as a fraction so we can apply our L'Hopital's. So I'm going to leave t on top, and I'm going to switch this to e to the negative t on bottom. And there is a negative out front, so we'll deal with that afterwards. That's a negative t. It's kind of hard to see. There we go. So now if I plug in negative infinity, I get negative infinity on top, and I get what on bottom? Positive infinity. So I can apply L'Hopital's. So if you have trouble showing your work in a clean way, you need to work on that. Okay, these problems involve multiple steps that you're going to work out as you're going through it. So if I apply my L'Hopital's here, I get 1 over negative e to the negative t. Good. So now if I plug in negative infinity, this turns into e to the infinity, which is infinite. And it's a negative, but that's not going to matter because 1 over a negative infinity is 0. So that actually goes to 0. This one here we said goes to 0, and this one here is -1. So what's my answer to my limit then? -1. So is it convergent or divergent? Convergent. Okay, it actually converges to -1. So questions there? All right, the next problem is like the 2-step one. We'll save that for tomorrow, and then we'll have a work day tomorrow on part 1. You can definitely start your homework tonight. That way you don't have as much tomorrow. I don't know how long these will take you. But this is the part 1 stuff where you have an infinity on your limits. So I think everyone can see that, right? Page 551, 5 to 25, every other odd. And if you have trouble with them, you can always ask tomorrow in class too. But this one here, what the question is on that next page, it goes from -infinity to infinity. So what we have to do is split that into 2 integrals and then solve each integral separately. Okay? Any questions? So tomorrow we'll finish the notes, and then we'll have a work day on part 1. And then Monday we'll move on to part 2 of this, which part 2 is not really harder necessarily. It's just harder to identify on the AP test that you have to do this to it. So that's where people get caught.